Hi, my name is Brian, and thank you for joining us for our third lesson about weather. This is a third grade lesson about weather. When we talk about weather, we're usually talking about clouds and rain and maybe reading weather maps. These lessons are a little bit different because we're really trying to understand what causes the weather and understand some of the things that are happening. Maybe you've learned about matter, and you've learned about matter that it can be visible or invisible. And it's that invisible matter, things like gases that we can't see, that cause so much of the weather that we actually see. So we've had two other lessons so far. In lesson one, we learned that air has weight. Because it has weight, it can exert a force. We learned that all the weight of the atmosphere is called atmospheric pressure, and it pushes in all sorts of different directions. In lesson two, we learned that particles that are warmer move faster. We also learned that water sticks to itself. And because water sticks to itself, if you slow it down, water molecules or water particles will form groups that we call droplets, or maybe small groups that we think of as fog. And if you speed them up, the water particles get enough energy that they can escape each other. They move fast enough that they overcome their attraction. So we're going to look today at the last detail here, which is thinking about how pressure could cause weather and looking at differences between high pressure and low pressure. It's important to consider with pressure that there's always two different areas of pressure. A balloon is nice because it kind of gives us a boundary. It gives us a barrier where we have one area of pressure on the outside of the balloon, and we have a second area of pressure inside of the actual balloon. So if you think about the process of blowing up a balloon, you know that you add pressure by blowing air into the balloon. And so that gives us a nice example of what pressure is. If we want to come up with a definition for pressure, pressure is just how hard gas particles push or hit the side of the wall or the containers. So there are gas particles that I put in here when I blew up this balloon. They're pushing on the outside. Now, if they were just pushing on the outside, then this balloon would keep getting bigger and bigger and bigger and bigger and bigger, even if I only added this amount of air. So there must be force pushing back against the balloon that's keeping it from getting just bigger and bigger and bigger and eventually popping. And there is another force, and that's the air pressure. So just like we talked about before, all of the gas from the atmosphere is pushing this balloon and keeping it from getting too big. All right, so we're going to look at another set of examples today that all compare high pressure and low pressure and how pressure causes gases to behave. So we're going to go to the lab for the first of these demonstrations. So let me get the cameras switched over, and I will see you in the lab. Okay, so what we have today is a pie plate. The pie plate has a pair of birthday candles in it. I just used 2 candles to make it a little bit warmer. Inside the pie plate is some water. It's got blue food coloring in it, but it's just water. It's not Jello or anything like that. It's just water. And then the birthday candles, I have some Play-Doh stuck in the water as well to hold the birthday candles up. The last thing I'm going to need here is this container. This container has nothing inside of it. It's just a container of air. There's a couple drops of water from some tests I did. And so let's think for a moment about lighting these candles. We know that fire is warm. And so we also know that above the candle, we saw in lesson 2 where I can feel some warmth. The air particles are moving faster. And over on the side, right where I'm kind of pinching here, air particles are moving slower. So we're going to do a quick demonstration where I'm going to just place this container over the candles and below the surface of the water. So this time I'm just going to demonstrate what will be happening. I'm going to place the container into the water like this, except for it will be with the candles inside of the container. That was just in case you want to try this at home. All right, so let's test this. This has to be done quickly, as I discovered a moment ago. So I'm just going to quickly push the candle over the containers and think about what you expect to happen if I cover these candles up with this glass cup. All right, ready? 1, 2, 3, go. All right. So if you're like me, I kind of had an idea that the candles would go out. I've seen someone do something like that before. But what I didn't expect was this water to go up inside the container. Now let's think about why water would go up inside a container. I learned something that always helped me when I was trying to come up with good explanations for things that I saw. I had a teacher once tell me that there's no such thing as suction in science, or science never sucks. So what we would not want to say is that we wouldn't want to say that the water had been sucked up inside of this cup, because science never sucks. There's no suction in science. So that means that something must be pushing the water up into the container. So we have a couple questions on our activity page 3.1 that kind of help us to understand and guide us through this. So the first question here is, what caused the temperature to change during the demonstration? Well, I think we have a pretty good example, or a pretty good idea here. The temperature was hot to begin with because the candles were on. And when the candles were lit, they made heat, and so there was a region of hot air inside of the cup initially. But pretty quickly, if you rewind the video, we'll see that those candles go out. And so if the candles go out, now the air inside of the tube has cooled down. So we went from hot air with particles moving fast, as we saw in lesson 2, to cool air where the particles move slow. Now, let's remember how pressure works. Pressure is pushing. So this next question about the demonstration is, what else changes as a result of the temperature change? What we have evidence of here is that when temperature changes, when the air inside of this container goes from hot and fast-moving particles to cool and slow-moving particles, the pressure changes. Let's go back to our definition of pressure to understand why. Pressure is how hard the particles are hitting the side of the container, and the last side of the container is also the water. So there's some particles in the atmosphere that are pushing down on the surface of water, and there's some particles inside of the container. They're pushing down on that inner surface of water. When they're moving fast, they push down real hard on that surface of water, and they push down hard enough that they actually keep the water outside. In fact, you might have noticed that when I first put the cup over here, there were bubbles that were escaping, and those were gas being pushed out because there was hot air trapped in here. I did it quickly enough. Once the air cooled down, though, the particles slowed down. They couldn't push down on this water any longer, and so the water rose up inside here until those particles got crammed together and they were able to push hard enough to keep the water from rising anymore. So what we see here is a connection that when molecules or particles are moving fast, particles exert a lot of pressure. Moving fast inside here, they can keep that water pushed down. The moment the candle goes out and the particles slow down, the water is able to get pushed up inside here. Now it's getting pushed up inside here because air pressure pushes down on the outside. All right. So we have a series of investigations now for the remainder of this lesson. And most of these investigations don't take very complicated materials. So I'm going to kind of work through some of the key points of these investigations, but I really encourage you to try to do as many of them as you can at home. All right, so I'm going to slide this out of the way. And we're just going to keep using the lab camera. So the first investigation just has us take our hand, and then we're going to place a drop of water on top of our hand. There, so I have one drop of water on our hand. Now I'm going to watch this drop of water for a while, but I'm also going to make observations about what I'm feeling. So what I can feel is that where the drop of water is sitting, my hand is cold. I can feel coldness from the water. I wonder if, even if I used warm water, if it would still feel cold. I wonder if I used things other than water, like maybe a drop of rubbing alcohol, if it would feel as cold or colder. I wonder if different liquids that are thicker, like syrup, if they'll feel as cold. So I wonder if all liquids have the same feeling. I wonder why it feels cold. Now, some of these things we can understand. We have some questions to think about. The water on your hand changed from a blank to a blank. Well, I still see water on my hand. I see a drop of water, and I know that drop of water on my hand is a liquid. So I've got a pretty good starting answer. Now, if I sat here long enough, I think that water drop would go away. But one thing I know about matter is it can't just disappear. What I've learned is that there are different types of matter. There's solids, liquids, and gas. So I think when this drop goes away, it's not actually just disappearing. I think it's turning into a gas, and gases are invisible, so I just can't see it anywhere. But it would still be bouncing around in this room that I'm recording in. All right, station 2 has me look at the outside of a cool glass. So I've got this cool container of glass here. It's cold. And if I look at the outside of this, what I can see, if I look carefully, are some droplets. And the droplets are even easier to see if I've put my hand there and maybe they've all collected. So I can see a droplet right above this E here that's starting to run down the glass. There we go. So I can see a lot of water droplets. Now, this happens because water vapor. Now, what is water vapor? Well, water vapor, to remind you, is water that's escaped. It's no longer trapped as a liquid, and it's become a gas. It's that invisible water. So on that last demonstration with the drop of water on my hand, it went from water on my hand to gas, and some of the same water that was on my hand, it disappeared, but it would now be stuck to this glass. We know that water just keeps cycling over and over. So it was inside of my room here because it left my hand, became water vapor. Now some of it might have even become these drops of water I'm seeing on the side of the glass. This happens because water vapor in the air changes from well, now we're going the opposite direction. It was water vapor, which is invisible, and it becomes a liquid. It was a gas. And that process where we go from a gas to a liquid is known as condensation. So I've had evaporation and I've had condensation. Station 1, I saw evaporation, and station 2, I saw condensation. There's one more term that you may have heard of or you might see in a reading called vaporization. And vaporization is what happens when you boil water. So when you add a lot of heat and it boils, you're turning it into you're vaporizing it, as opposed to evaporating is usually the word we use if it's just normal temperatures that it's just slowly disappearing. All right. My next station here involves my balloon again. So with my balloon, we already talked about the fact that there's two areas of pressure. There's pressure inside the balloon that's pushing out, and there's pressure on the outside of the balloon pushing in. I'm going to use my hands here though, and I'm actually going to change the pressure inside of the balloon. So what I'm going to do is, I have this large bottom part of the balloon. I'm going to squeeze it, and let's see what happens. Hopefully I don't pop the balloon. Look at that. I can make the large part go to the opposite side. So here I'm kind of helping out air pressure. It returns back. So what I'm doing is I'm squeezing high, or I'm squeezing down at the bottom, which creates high pressure, and it pushes all the air in the bottom of the balloon up to the top where there's lower pressure. It's actually a lot like that first demonstration that we did. If we think about this, when I'm going to try to set it up the same way. If I squeeze the top of this balloon, that's a lot like what was happening when the candle was lit. There was high pressure at the top. Now, when the candle went out, that's like me stopping squeezing. So if I stop squeezing, we know that air is going to come back up and fill the top part of this balloon. Flip this over, it might even be easier to see. When it was hot inside there was high pressure at the top of the container, at the top of the balloon. When we let the candle go out, that takes away the high pressure because the particles slow down, and so it pushes the air, in this case the water pushed the air to the top of the container. So when we when we squeeze the balloon, we saw that squeezing the balloon causes the shape of the balloon to change. And the shape of the balloon changes as the air moves from where there's high pressure, where I'm squeezing, to the lower pressure side. If I stop squeezing, the air can return back to there's even pressure. So we see that air always moves from high pressure to low pressure. Our last demonstration here is going to involve a container of water. So it's kind of hard to see the water. It's actually not as hard as I thought it might be, but I'm just going to add some food coloring so we can definitely see that there's water there. Stir this up. There we go. Try to get more even color. And I'm also going to use this cup of crumpled up paper for this demonstration. All right, so I have a piece of paper in here. Now, you might have done something like this before, but if we take this cup and we push it down, we can actually see the paper going underneath the water there. I want you to predict what happens when I lift the cup back out of the water. So I've had it underneath here. Hopefully the paper doesn't fall out. And if I lift the cup out of the water, we know what paper would look like if it got in wet food coloring. But this piece of paper is still completely dry. So I still have a nice dry piece of paper here. You can do that again. This is also a great one for you. Try at your home. You don't even need the food coloring. Just get a cup and a container that fits in the cup. Hold it upside down. Push it underneath the surface. I can see that the paper is all the way under the surface of the water. And the paper still comes out dry. So station 4, what did we observe when we pushed the cup underwater? We observed that the water level went up because the cup took up some of the space. We also saw that the paper came out dry, so water must not have gone inside of the cup. Now, water did not go inside of the cup because the cup was already full. What was the cup full of? Well, the cup had paper inside of it, but I wouldn't say it was full of paper. What was it full of? It never got full of water. We know that because if it got full of water, the paper would be wet. I remember. It's full of something invisible. It's full of gas. Gas exerts a pressure. So I guess when I push down on this, it's full of invisible gas. And that invisible gas pushed the water away so it couldn't fill up inside of the cup.
So one of the things that I like to think about is what science is and what makes science different from social studies or science different from math or English. And to me, what science is explaining things. And scientists have tools that they use to explain things. And one of those tools are models. Now, models can look lots of different ways. Today, we're going to do a model, which is a drawing, but models always have 3 different parts to them. They have the stuff, and by stuff, I mean the things that were acting together. They have the relationships, and the relationships are, how is this thing impacting this thing? Or what is the effect of this part on another part? And then the last thing that models always have is a connection. And that's because models should connect to something in the real world. And so we're going to do a model today. We're going to have the stuff, the relationships, and the connections to explain this demonstration we did. And that was the demonstration of taking the cup, putting it upside down in a container of water, and having it come out dry. So models can help us to figure out what's important. So let's think about this container. The shape of the container is not too important. What is important is that there's water inside of it. So I'm not going to worry too much when I draw this. About what shape my container has. I'm really just going to worry about whether or not my container has water in it. So that's one piece of my stuff, is the water. Another piece of my stuff is the cup. Now in this, I'm going to try to draw it so that I can see my cup upside down. And because we don't have a lot of time today, I'm not going to draw a group of drawings. I'm just going to draw one drawing to explain what's happening. If you've ever seen a comic strip, comic strips might tell a story in pictures. Those are really helpful when you're doing models. We're just going to do one picture today. And the last piece of stuff that we could see is the paper. So I'm going to put my ball of paper up into the bottom of the cup. Now, what we really wanted to be able to explain is I can put the fact that I can put this thing all the way underwater. And even when it's all the way underwater, the paper stayed dry. So scientists use models to explain things. And in science, there's a special word for explanation. And that word is theory. So the last piece of stuff I need for my explanation is the gas. Because if you remember, pressure is caused by invisible gas. So what I know is that when I put this cup underwater, the paper stayed dry. That means that the water might have gone around the outside of the cup, but the water did not go up inside the cup. So there would be another edge of the water down there. How do I explain this? Well, it's very similar to the way that a balloon fills up. When you blow air into a balloon, then that air pushes on the sides. So we're going to draw some pieces of air. And when these pieces of air are moving around, so I'm going to give them little tails to show that they're just bouncing around in all directions. Some of the pieces of air are pushing down on the water. Some are pushing on the sides of the cup, but it's those pieces of air that are pushing down on the water that help to keep the water out of the cup, or that do keep the water out of the cup. So this is a model to explain why the cup stayed dry. Let's review the three parts that a model should have. The model should have the stuff or the components. So let's think about what the stuff was here. The stuff was the water, the stuff was the paper, the stuff was the gas. So we had four pieces of stuff. A model should have relationships between those. So I know that the air pushes on the water, and that keeps the water out of the cup. And then finally, models have connections. So this model connects or shows me something about and explains how something works in the real world. There's even connections where this model can explain other things. Like there are types of spiders that build webs, and in these webs they trap air just like this, and those spiders can work like scuba divers and go underwater because they have this trapped pocket of air. So what I think would be a good challenge is take one of the other demonstrations we've done, whether it's squeezing the balloon or some of the other ones, and see if you can draw a model, figure out what pieces are interacting, and what causes that thing to work. We'll see you in the next video. Good luck on that model.